Alright, so I'm going to try to give a quick rundown on periodic trends. First of all, if you don't have a periodic table nearby, you need to get one, because I'm going to be referencing that a lot. There are three main trends I want to talk about. There's obviously more, but if you can get these three, you can pretty much figure out the rest of them. And these are the main three we're going to talk about anyways. The first one I would like to look at is atomic size, or atomic radius. The radius, of course, of a circle being the distance from the center to the outer edge of the circle. So for the atom, it'd be like the nucleus to the outer edge of the atom. When you think of atomic size, a lot of times you would start thinking of the mass immediately. So you would think, okay, well, hydrogen's probably the smallest, and number 118 is probably the largest. And that is true as far as mass is concerned. So it's 118 is the most massive, hydrogen's the least massive. But that's not size. We're kind of looking more at the like volume of the atom, actually. And to understand this, you kind of have to think of, think of the Bohr model of the atom. So it's sort of like an onion, it has rings. And you have to think in terms of protons per energy level. So if in the atom, the protons are attracting the electrons and keeping them, they're reining them in, if you will, the more protons you have per energy level, the faster you're going to be able to, or not faster, the better you're going to be able to hold on to them. So for instance, if you look at lithium, okay, lithium has two energy levels. So if I were to try to draw lithium here, I would draw something sort of like this. It's got 3 protons and 2 energy levels. Well, as you go across that row, across that period, you end up at neon. Neon also has 2 energy levels, but neon actually has 10 protons to rein in those 2 energy levels. So neon is actually going to look sort of like this, smaller, because it has more of those positive charges, more of those protons to rein in those energy levels that are filled with electrons. So obviously neon has more electrons as well, so you have to think of it in terms of protons per energy level. So if you think in terms of that, the atomic size is going to increase as you go down and to the left on the periodic table, because as you go from left to right across the periodic table, you're getting more protons per energy level. But as you go top to bottom, you are gaining more of those rings. If you're thinking of it in terms of an onion, you're gaining onion rings as you go down, so it's obviously going to get bigger. The next one we're going to talk about is ionization energy. And an ion, of course, is a charged particle. When we're talking about atoms, if you change the number of protons you have, you're changing what element. So the currency that atoms deal in are electrons. So we're going to add or take away electrons. We're adding or taking away negative charges. So to make a negative ion, you would add electrons. To make a positive ion, you'd take away electrons. So the ionization energy is the energy it takes to remove an electron from an atom. And typically we're talking about the outermost electron. So there's the first ionization energy, the second, the third, the so on and so forth, all the way until you don't have any more electrons. The first ionization energy is the energy it takes to remove the outermost electron. The second ionization energy is the energy it takes to remove the one after that. The third ionization energy is the one after that, and so on and so forth. So we're just looking at the first ionization energy. And what you have to do is think about the pull that the protons have on each electron. So for instance, I'm obviously going to oversimplify this, but francium, okay, it's got 87 electrons. Do you really think that it's going to be able to hold on to all 87 that well? You have 7 energy levels, a ton of electrons. It's just not going to have that tight of a grip on the electrons. Not only does it have a lot of the electrons, but the nucleus is now 7 energy levels away from that outermost electron. So that 87th electron is just out there by itself, far from the nucleus, with a whole lot of electrons in between. So it is not going to be held on to very tightly. Helium, on the other hand, helium is a noble gas, and it's only got 2 electrons. So it's going to hold on very tightly to its 2, first of all, because it only has 2 that it's got to worry about, and second of all, they are very close to the nucleus. They're both on the first energy level. And third of all, it's got that full outer shell, so it's a noble gas. So ionization energy is going to actually increase up into the right, okay? Now, looking at left to right for ionization energy, think about sodium for a minute. In order to get a full outer shell, sodium has 2 options. It can either lose 1 valence electron or it can gain 7. Which do you think it's going to do? It's going to want to lose 1. Okay, gaining 7 electrons is too much work. So do you really think that sodium cares if it loses that outermost electron that much? No, not really. So it's going to be a lot easier to take one from sodium versus taking one from something like chlorine, where chlorine just wants 1 electron. It just needs to get 1 more. It can do that, or it could go ahead and lose 7 valence electrons to become a noble gas. But losing 7 is way harder than gaining 1. So chlorine's going to hold on to what it has very tightly because it actually wants to get 1. Now, if you'll notice, that's a perfect combination. Sodium wants to get rid of 1. Chlorine wants to get 1. So this is how we get table salt, NaCl. It just works out very nicely. So going down the periodic table, you're getting more and more electrons. They're getting further and further away from the nucleus, so it does not take as much energy to remove the outermost electron. Going from left to right, you're getting closer to having an octet, so the atoms tend to hold on to their electrons more tightly than the ones on the left side. So the ionization increases as you go from left to right. Last one, electronegativity. That is defined as a bonded atom's ability to attract electrons to itself. A bonded atom's ability to attract electrons to itself. And simply, there's more to it, and we will discuss this in class, but simply speaking, it's how well an atom can attract electrons to itself. So which ones do you think will want electrons more? Well, we kind of already had this conversation. The ones that are really close to getting an octet by gaining electrons are the ones that are going to probably be more attractive because they only have to get 1. So for instance, fluorine, chlorine, they only need 1 electron, so they are going to be very attractive to electrons. They're going to attract electrons to themselves. So going from left to right, it's going to increase. Sodium does not want another electron. It wants to get rid of 1, so it's not going to be very attractive to, it's not going to attract electrons very much. Top to bottom, once you get toward the bottom, there's so many electrons that are there. It doesn't care if it gets more or not. Francium has 87, for instance. Does it even keep track of them all? So you're going to go down in electronegativity as you go from top to bottom. So just like ionization energy, electronegativity increases as you go up and to the right. I know that was kind of quick, and we'll talk about this a lot more in class, but I thought I would make this for those of you that missed